Hello, everyone. So in this video, I want to give an introduction to centripetal acceleration. That is the acceleration that objects experience when they're moving on circular paths. And so to start off, I want to give this little example here. So I've got the Earth and the Moon. In this toy model, I'm going to assume the Moon's orbit around the Earth is circular, which it's not. It's a little bit elliptical. But let's assume that it's circular, which is close enough. And we'll get all the intuition we need out of this assumption. So a question, does the moon accelerate? Well, there's a couple ways to think about this. In some sense, it seems like a confusing question because the speed of the moon stays pretty much constant. It doesn't change its speed as it paths across the sky for us, apparently. But certainly the velocity vector does change, because if I have some initial velocity for the moon in this direction, let's say, and then the moon travels to, say, this point right here, the velocity vector has changed. So the velocity will stay tangent to the circular path that it's on. It's always moving in the direction of that red path if it's moving on a circular arc. So in that sense, yes, the moon is accelerating because the velocity vector is changing. Even if the magnitude of this vector and this vector are the same, so that the speed's the same, it's accelerating because the direction of the velocity is changing. So as long as there's any change in velocity, that means that there's some acceleration. In this case, if the speed of the moon is constant, the acceleration represents just a change in direction of velocity rather than a change in speed. So what sort of acceleration would cause that? How do you get a change in velocity without a change of speed? Well, you get that if the acceleration is perpendicular to the velocity. So if I have an acceleration vector that points perpendicularly to the motion, so if I have some acceleration vector that points that way here, and some acceleration vector that points, let's say, try to draw it the same length, close, and some acceleration vector that points that way for the final case of the moon that I drew, then I always have change in velocity that turns the velocity in the direction of the circle that it's trying to move on. You can see what would happen here. So if I have velocity starting out this way initially and some acceleration this way, the acceleration represents how the velocity changes over time. So this velocity will change in this direction over time. So it's not changing the magnitude of the velocity. It's not changing the velocity in this direction or this direction, which would speed it up in this case or slow it down in this case. It's just pulling it down. So all that's doing is pulling the velocity down. And in this case, there's a perfectly reasonable physical reason why the acceleration would be doing this, because of gravity. So Earth is here, the moon's here. There's some force of gravity that always pulls from the center of the moon to the center of the Earth. And so as the moon's position changes, the force changes and the acceleration vector changes as a result. And if the moon is moving on a circular path, that change will be just so that the velocity and the acceleration always stay perpendicular to each other and create this relationship where the acceleration is only ever changing the velocity. So let me answer this question. Yes, the moon definitely does accelerate. But when the acceleration is perpendicular to velocity, the acceleration just changes the direction of velocity. Okay. And you can see that's a condition for having a circular path. If the direction of V, if only the direction of V changes. Okay. So there are some interesting physical things to think through here. So why do we have a circular path in the case of the moon orbiting the Earth? Why do we get a circular path ever? there's two competing things here. One is the moon wants to keep going in the direction it's going. That's Newton, that would be Newton's first law, right? So if I have a moon, oops, that's the wrong thing. If I have a moon here and it has some velocity in this direction, it wants to keep going in that direction, and its velocity will only change if there's some force acting on it. That happens to be gravity here. So gravity starts turning the moon. But how much does it turn the moon? If gravity is weak, then the moon will turn a little bit, but mostly keep going in the same direction. And I could get an orbit that doesn't look circular, that basically looks like a flyby where the moon comes in, gets turned a little bit, and kind of keeps going. Oh, here we go. So some orbit that looks like this maybe, right? Where it's not circular. It's either a big ellipse or a hyperbola, as it turns out. Or if I had kind of a slow velocity relative to how strong gravity was, then the moon is mostly just getting pulled down. And so it has a little bit of velocity and it's getting turned really quickly in, and I'll end up with something that looks like this, another kind of elliptical type orbit. But if there's a balance between how big this velocity and how big this acceleration is, then I can get this nice circular path. And we're going to try to derive the condition for that in this video. Okay, so when do we get circular motion? So let's try to figure that out. So let me make some stuff up here, define some variables. All right, so I'm going to draw some lines. So, and I'm going to erase my accelerations so that my picture doesn't get too cluttered. But we'll remember that it's accelerating towards the center of the circle here. So I'm going to draw a little triangle here and here. So let's say that the moon's gone from its initial position as I drew here to its final position as I drew here. There's some angle that it swept out. We're going to pretend that that angle is really, really small. So we're looking at infinitesimal changes in the moon's position here. We're going to define a radius here as well. So there's some radius that represents the distance from the Earth's center to the moon's center. So there's some circle that the moon's moving on of radius r. And also there is a path length that the moon has undergone. I'll call it ds from there to there. So ds is an arc length. And you may recall, or may not recall, from math that you can always write an arc length as the radius times the angle swept out. And I won't derive that here, but it's not too hard to derive, and we can go through it later if you want. Okay, so that's one triangle. There's another triangle that I can draw as well. So if I take the velocities and put them tail to tail, so there's a VI here, and then there's a VF that points like there, let's say. These vectors have the same magnitude, but the difference between them has to do with the acceleration. The acceleration points perpendicular to the initial velocity here. And really will be the vector a dt. So there's some acceleration times time that represents the change in velocity. I can write it this way, delta v, which represents just the difference vf minus vi. So that's a dt. But if I do some geometry, I could figure out that this angle is actually d theta 2. And you can prove that to yourself geometrically if you like. I'll just take it as true for right now. And you can convince yourself that it's true. So this is another triangle. If I look at this triangle, it's another one where I've got some radius where this vector and this vector have the same magnitude. So, and I'll call the magnitude of this just v, and the magnitude of this just v. They have the same magnitude because we're looking for the condition where this motion is circular and where the speed never changes, but the velocity just changes direction. So this is another case where I could kind of apply this arc length thinking, where the magnitude of the radius of this circle that it's on for this triangle times the angle swept out is equal to the arc length here. It's that same sort of approach. And so I have a dt, and now I'm talking about magnitudes. So I'm just going to write it like this. Magnitude of the acceleration vector a, dt, is equal to the magnitude of the velocity times d theta. All right, so what does that do? Well, this is kind of interesting because I've got these kind of two relationships that have d thetas in them. And I'm trying to figure out how big the acceleration has to be given the velocity for my circular condition. I've built my circular condition into this by assuming that this looks like the arc length of a circle. That's how I built my circular motion condition into this. I'm going to take this equation and note that it says that d theta is the arc length over the radius. And then I'm going to take that and plug it into my second equation down here. And I'll get something that looks kind of like gobbledygook, but it'll go somewhere. So then a dt is equal to v ds over r. All right, so let me move some stuff around. So a is v over r ds dt. So I've got the acceleration as v over r ds dt, but this thing is an arc length over a time, an infinitesimal arc length over a time, which is just the speed again. This is telling me the rate of change of the position of the moon along the circular path. So this thing is just the velocity, the magnitude of the velocity again. So this is v over r times v. And so the result I end up with is the magnitude of the acceleration is v squared over r. All right, so what does this mean? This means that in the case of circular motion, the acceleration of the moon or any object undergoing motion along a circular path has to have that acceleration in the direction of the center of the circle. So this, I'll write that too. This points towards the center of the circle. And the r there represents the radius of the circle that the moon, in this case, is moving on, or it could be whatever is undergoing circular motion. This is often called centripetal acceleration. Centripetal, I guess I'll write that too, and I can use a different color because that's fun. Centripetal petal acceleration. And centripetal means center seeking. That's kind of like a direct consequence of what's physically happening here, where there's some force that's pulling the moon towards the center of this arc. So it's this center-seeking acceleration, where the reason why the moon's turning is because it's being pulled towards the center, which is the Earth in this case. There's lots of other examples you could use for centripetal acceleration. If you put a brick on the end of a rope and swing it over your head, then the force on the brick that causes the brick to move in a circular arc is the tension in the rope. That would be the force that causes the centripetal acceleration in that case. And there's lots of other examples that you could come up with where this is relevant. But this will always be the condition that is met if something is moving on a circular arc. Okay, so I want to give an example of how to apply this. It's kind of an interesting thought experiment as well. So give me one sec to draw that out. All right, so here's an example. I've got a picture of the Earth, or drawing of the Earth over here, and I've got me standing at two different locations on Earth. So in one case, I'm at the North Pole, and in another case, I'm kind of way out here in the ocean, maybe at Hawaii or something like that, or I don't know, Far East Russia. I'm not really sure. But in any case, on one case, I'm on the equator. In one case, I'm right on the axis of Earth's rotation. And the question is, if I were trying to measure my weight in both of these locations, how different would the scale readings be? And a reasonable question to ask in response to that is, why would the scale readings be different at all? Shouldn't you just get the same thing every time? If you're standing on a scale, you register your weight. Well, let's think through why that would be. So if I have, here's my scale, I'm standing on my scale, and here I am. Normally, the argument goes, I have some weight acting on me. That's the force of gravity on me. And then there's some normal force acting on me. And normally the argument goes that if I'm still, if I'm not accelerating, then the normal force must be equal to my weight. And what a scale registers is my normal force, how hard I'm pushing into the scale. So therefore, when I read the normal force off the scale, I'm really getting something that tells me my actual weight, the actual force of gravity on me. That's fine. So the argument relies on the idea that if I applied Newton's second law, that is the net force N minus Ng is equal to my mass times acceleration, that acceleration is 0. If acceleration is not 0, then the normal force will have a different value. It won't be equal to my weight anymore. And you can see that this requirement, that in order to move on a circular path, an object must be accelerating, applies to one of these cases where my weight's being measured. If I'm at the equator, I am in fact moving on a circular path because the Earth is rotating. And so the Earth rotates, and I rotate with the Earth. I go the entire circumference of the Earth in one day. So I have some rotational speed here. On the other hand, if I'm here standing at the North Pole, I'm kind of rotating in place, but I'm really not moving on a circle. I'm not moving around some center. And so I don't really have any centripetal acceleration up here, but I do have some centripetal acceleration here. I have to. If I didn't have acceleration that pulled me toward the center of the Earth, then I would just fly off into space at the velocity that I have standing here on the surface of the Earth. So there has to be some acceleration pulling me into the Earth to keep me rotating on a circle. So let's work out what that looks like. So if I'm on the equator, I can work out what my centripetal acceleration has to be. So my acceleration has to be v squared over r. R here represents the Earth's radius. So the distance from the center of the Earth to my position on the equator. If I wasn't at the equator, I would be moving on a different circular arc that would be smaller, but would still be moving on a circular arc, rotating around the Earth's axis. But I put it on the equator so that we didn't have to think about geometry at all. We could just use the full Earth's radius here to represent the circle that I'm moving on at the equator. But how fast am I moving? Well, my speed is going to be how far I go over how long it takes me to go. So I go the full circumference of the Earth, that is 2 pi times the Earth's radius, in one day. So 1 day is 24 hours times 3,600 seconds per hour over Earth's radius again. If you work this out, which you can look up Earth's radius, which is like 6 million kilometers, something like that. Or excuse me, 6,000 kilometers, 6 million meters. If you work it out, then you end up with like 0.034 meters per second squared, which is a small number, but maybe bigger than you would expect. That's not an acceleration so small that we can't measure it, for example. So if I'm standing at the equator and try to measure my weight, actually the equation of what I would get on the scale goes something like this. So the normal force minus my weight is equal to ma that I just calculated. So my normal force is actually my mass times gravity plus that centripetal acceleration. Now, I got to be a little bit careful here because which way does the acceleration go? It actually goes down. So the acceleration pulls me down towards the center of the Earth. And so in my coordinate system that I've kind of used by default, Down is negative, up is positive. So this acceleration value should be negative, the value I calculated here. And so the normal force is slightly reduced compared to what it would be if there was no centripetal acceleration. So my weight is slightly reduced by a little bit. So if I assume that G is 9.81, then instead of having the scale reading be my mass times 9.8, I get 9.81 minus 0.034 here, something like that. So that's a reduction of like, you know, a little bit, 3%, something like that. So I'm 3% lighter on a scale at the equator than I am at the North Pole, which is kind of interesting to know. So this is an example of how you can use centripetal acceleration to start thinking through problems, a way to apply it to a specific problem. And I'll leave it there. Okay, see you soon. Bye.